Hey guys, so we already did the first part of chapter 18. So today we're going to do the last part of chapter 18 notes. So after today, we will be done with chapter 18 notes. We'll do a little practice in that packet that I gave you before break. And once we're done with the packet, I'll give you some review problems and we'll get you ready for your chapter 17-18 test. So we're almost at the end of this chapter. But before that, I wanted to show you guys what this student version of the notes looked like that I provided to you. So I did put the slides on a PDF for you guys, just so you guys could use that software Cami to edit it. Oh my gosh. If you want to. So this is the PDF. This is what it looks like. So if you want to use Cami and type on it or draw on it or write on it, whatever, just make a copy of this PDF that I linked in the agenda and open up Cami or just search Cami and open this up once you're logged into Cami. If you need to know how to use the Cami software, remember that I did put a little mini tutorial in Google Classroom, and I want to say that it was on April 16th. So just scroll down to April 16th and you should be able to see that Cami tutorial video linked in the stream on Google Classroom. Okay, so let's get started with the notes. So I just want to show you what they looked like in PDF form. But you can either edit it with Cami, you can type your notes on a Google Doc if you want to, you can print this out and write on it, or you could do it the old-fashioned way and just open up a notebook and write everything down. If you decide to do the last thing, then I would recommend pausing the video every so often. So let's get this started. Okay, so the first thing that I want to talk about before we move on is I forgot to mention the differences between the graphs if the products have more energy or less energy than the reactants in one of these reaction progress graphs. So I already told you the parts of this graph. So we have the reactants over here, we have the products over here. This is our activation complex, and this is the amount of energy that we need. This is our activation energy. What we have to go to from the reactants to the activated complex. And so we already did that in the last video. So if you're a little fuzzy on it, go rewatch that part in the last video that I posted. And but I wanted to show you guys the difference between endothermic and exothermic graphs because there is a difference. So when we have an endothermic graph, so remember in endothermic reactions, which way is the heat going? The heat is going into the system. So I'm going to say heat in, endothermic in, because in endothermic we're entering with the heat in system. So with endothermic reactions, heat is going in, so heat is energy, and so heat is going in, and the products will have a little bit more energy at the end. And so I want you guys to know that the energy of the products is greater than the energy of the reactants in an endothermic reaction, and delta H is positive. And remember, energy is gained here because energy is going in. In exothermic reactions, the energy of the products is lower than the energy of the reactants. This looks a lot like the graphs I showed you last week where reactants were up here and then we went up and then we went down for the products, and we kind of went lower than the reactants for the products in our graphs last time. And so this would be an exothermic reaction, and this is where heat is exiting, right? Heat is being lost. So the energy is lower because we're losing heat as energy, and then the energy of the reactants is going to be higher. And then delta H is negative because obviously this is an exothermic reaction, and we know that exothermic reactions have a delta H that is negative because energy is lost. So I wanted to point that out and add this to this video's notes so that was clarified. But now we can move on. Okay, so now we're going to get to the last couple sections in chapter 18. This is about entropy and free energy. And so I want to mention here that entropy sounds a lot like enthalpy, but they're very different. So remember, enthalpy is delta H. Okay, and that's the amount of like heat that's in the system. And entropy is completely different. I'll define it later, but enthalpy is delta H, but entropy is delta S. And so I wanted to differentiate between those two vocabulary words before we moved any further, because honestly, to me, enthalpy and entropy look very similar. Sometimes even I mistakenly swap the words and I'm like, oh no, that's not what I meant, because they're totally different. So I wanted to mention that. Okay, so the first thing we're going to talk about in this section is our spontaneous and non-spontaneous reactions. So spontaneous reactions are reactions that just kind of occur naturally, and they don't really need any extra energy for help. And so spontaneous reactions favor the formation of products at, specific conditions. So this would be an example of a spontaneous reaction. We see a liquid being poured into another liquid and a reaction occurring without any additional energy being added. And so remember, that is the definition of a spontaneous reaction. It's a naturally occurring reaction that occurs without any extra energy being added, and it favors the formation of products. And remember, you can pause this video if you need extra time to type or write or, whatever. And then we get to a non-spontaneous reaction. So if a spontaneous reaction is one that occurs naturally and favors the formation of products, we can assume that the non-spontaneous reaction is a reaction that does not favor the formation of products and does not occur naturally by itself. So spontaneous reactions, they need a little extra energy. So I'm putting they need help in the form of energy. And so an example we have here is photosynthesis, because you might think, oh, photosynthesis occurs naturally. It occurs in nature. No, that's not how it works. Photosynthesis is actually non-spontaneous. And if you think about it, it makes sense, because photosynthesis doesn't happen without light, okay? And so, we have our carbon dioxide, we have our water, and those don't just make sugars on their own. They need help. And so remember that plants need light to survive. Light is the energy source for the plant to do photosynthesis. So the requirement of an input of energy for photosynthesis is light. So plants use light energy as their source of energy to do their non-spontaneous photosynthesis. And so, like I said before, in this one, spontaneous reactions favor the formation of products. So because of that, spontaneous reactions produce a lot more products, and a lot more products than they do reactants. And in this slide, I don't know if you guys went over this before I got here, but you can have reversible reactions where you have, so you have your reactants and you have your products. And so normally we see our reactants with an arrow to our products, but sometimes we see a reactant arrow to products and a product arrow to reactants. That means the reaction is reversible, and it can go, from reactant to product, or products can go back and become the reactant. So it can go, back and forth. So I hope you guys learned that, and I hope I'm not confusing you. But that's my little lowdown on reversible reactions, because that's kind of necessary to understand this whole slide right here. Because when we say spontaneous reactions produce substantial amounts of products, that means this forward reaction is favored here. So this one. So this reaction is favored where the reactants are creating products. And I just want to say that if this isn't completely clear, or you guys didn't do this yet, we're going to talk more about reversible reactions when we talk about equilibrium, and that's not in the next chapter, but the chapter after that. So we'll touch a little bit about that, hopefully, if we have time at the end of the year. But I just needed to mention this because reading this, you might think spontaneous reactions produce substantial amounts of products, obviously. But what this is saying is, this is not trying to be obvious. This is saying that like spontaneous reactions produce a lot of products. So they favor this kind of forward reaction where it's reactants to products, and they don't favor products to reactants. Non-spontaneous reactions favor products to reactants. So there's usually more reactants. And so that's why I felt that it was necessary to mention this. Another thing spontaneous reactions do is they release free energy, okay? And so, my face is always in the way. Okay. So they release free energy, and what free energy is it's just energy that's released by a reaction that is available to do work. And so sometimes what happens is a spontaneous reaction will be coupled with a non-spontaneous reaction. So what that does is, if a spontaneous reaction is one that gives off energy, and a non-spontaneous reaction is one that needs energy, it would make sense to kind of pair those reactions so that when the spontaneous reaction occurs and there's a release of energy, the energy that's released from the spontaneous reaction will go into the non-spontaneous reaction and make it happen because of the energy it has from the free energy, if that makes sense. But basically, the spontaneous and non-spontaneous reactions can be coupled if, spontaneous reaction gives off enough energy to the non-spontaneous reaction for the non-spontaneous reaction to occur. And so that's why free energy is beneficial. Okay, so now we're going to get to entropy, not enthalpy, so not enthalpy, which is delta H. Just remember that. It's different. So entropy is a measure of the disorder of a system. So ever since I learned this word in high school, and I learned what entropy was, that's a measure of the disorder of a system, I just think I cannot get out of my mind that it's just a measure of how crazy something is. So we'll kind of talk about the factors in a few minutes about what makes entropy, so, the disorder, increase. And it's just fun to think about, like, how can we make this crazier, or how can we make this more energetic? So stuff like that. So I like entropy because it's just a measure of how, like, crazy the system is. And so usually when we have systems, they like to have low energy. And so low energy usually means that the entropy is low, because if we have less energy, we have less craziness. Think of like a toddler. Think of like a kindergarten class where you have a room full of like little kids and you give them candy and they have all this energy and they're running around like breaking stuff, and so that there's a lot of disorder there. But think about, if they aren't given that candy, they don't have a lot of energy and they're just, walking around playing very nicely, the disorder of the room is very low. And so the entropy of that room would be low. So that's just kind of how I think about entropy. I imagine like a bunch of crazy little kids running around who had just eaten candy and have a lot of energy. So we have this law of disorder, and it states that usually systems tend to move in the direction of maximum randomness. So we have the physical and chemical systems that they want low energy, but at the same time we have this law of disorder where, our systems like to have craziness and randomness to help things progress. And so an increase in entropy favors spontaneous reactions. So this is more craziness equals spontaneous reaction. And a decrease in entropy favors non-spontaneous reactions. So if there's a decrease in entropy, you're probably going to have a non-spontaneous reaction. And so if you have an increase in entropy, then you're probably going to have a spontaneous reaction. So this is a really important slide for you guys to take note on, because there probably will be questions in the future. Well, I know there's going to be questions in the future about this, where it'll say, how can we, or a spontaneous reaction favors what? And so that would be an increase in entropy. So an increase in disorder. So just so you know, this is an important slide. So now we're going to kind of talk about what increases entropy and, what kind of decreases it. So the first thing we can talk about is going from solid to liquid to a gas. So usually for a given substance, the entropy, so the disorder of the gas is greater than the entropy of the liquid and greater than the entropy of the solid. So as you go from solid, liquid to gas, you're increasing the entropy. You're increasing the craziness, okay? Obviously, we see these nice little ordered particles in the solid. When we go to liquid, they get a little crazier, and then when they get to gas, they're like super crazy, and so they're super disordered. And so the entropy is high here, and it's higher than the entropy in this solid. So the entropy increases in reactions where solid reactants go from a solid state to a liquid or gaseous state, because we're increasing the disorder of the system. So that would be an entropy increase. And then I already kind of mentioned this. So if the entropy of gas is higher than the entropy of the solid, the entropy of the liquid is also greater than the entropy of the solid. Basically, the solid is very orderly, has low entropy. Liquid has moderate entropy, so moderate energy, moderate disorder, and then gas has a lot of disorder, a lot of randomness, with all those particles bouncing around everywhere. So you can also increase the entropy by breaking a substance down into its parts. So a good example of this is if you were to take, some salt and dissolve it in water. Because what do we know about when something's dissolved in water? So think about it like this. So if you have your solid salt, it's going to be a really bad drawing, I'm so sorry. So you have your NAs and your CLs there. And then when you dissolve it in water, I didn't mean to do that. Dissolve in water. Remember what the water does is it pulls apart the pieces of salt. So that, I have a little. So hopefully my picture is making sense. I'm going to change the color of one of these things. So this is the water. I'm so cliche, I'm making it blue. So these are the water molecules pulling apart the salt. And so this is a good example because here you have a big chunk of salt. You have a big crystal of salt, right? Even if it doesn't look big to us, the salt is made up of all these different atoms put together in a crystalline structure. When you dissolve that in water, the crystal gets broken up into smaller pieces than it was before because the water, remember, is polar and likes to pull on the parts of the crystal. And so it makes the crystal go into its ions, okay? And so we know its ions are what makes up the crystal. And so if we're just having individual ions in the water, obviously those particles are smaller than your crystal. And so thus the entropy is increasing. So increasing delta S, that's entropy. Okay, and so you can also increase entropy if you're creating more molecules than you had in the reactants. So basically what that means is if you look at this diagram down here, you have two water molecules, right? So you have two molecules, and then, through electrolysis, which is, the breaking up of water into its like parts, basically. So you get your 2 hydrogens, your 2 molecules of H2, and then your 1 molecule of O2. You now have 3 molecules here instead of 2. So entropy will increase if you have more molecules in the products than you did in the reactants. So obviously here we have 2 water molecules, and then we're going to 3 molecules total, which is the 2 H2 molecules and then the 1 O2 molecule. And so remember that spontaneous reactions involve an increase in entropy, and remember that spontaneous reactions also favor products. So that makes sense, because if we're favoring products here, we have more products, and increasing entropy would be a spontaneous reaction. So if we're increasing the reactant molecules, you can also think about it this way. So if we're increasing the amount of molecules as products, more molecules means more disorder, okay? So think about if you're babysitting 2 like 3-year-olds who are running around, that's a little bit less crazy than like babysitting 3 3-year-olds who are running around, because it's easier to keep track of 2 than it is 3. So 3 molecules is greater than 2, and that will be more disorder. And then the last way you can increase entropy is increase the temperature. We know that temperature is a measure of how much energy the particles have. So remember, when we're measuring when we're measuring temperature, it tells us what the average kinetic energy of the particles in that substance have. So remember, solids are going to have a low temperature because there's really low energy, but something like a boiling liquid is going to have a much higher temperature because those particles have really high energy, right? So as the temperature increases, the molecules have more energy, and more energy makes more disorder, okay? So as we increase the energy, we're increasing the temperature, and as the temperature increases, so does entropy. So here we have, just straight room temp water. It's like, it kind of has some disorder. As we heat it up, it has more disorder, and the particles are more moving faster. They have more energy. And then here, the water is boiling, and we have a lot more energy here, and so we have a lot more disorder. And so the entropy is going to be the highest in this one. And so these are kind of how enthalpy, the one we learned before. So remember, enthalpy is delta H, entropy is delta S, and then we don't have a free energy variable yet. So enthalpy, entropy, and free energy are related, and they can determine how spontaneous a reaction is. And so, the size and direction of enthalpy and entropy is kind of what determines if a reaction is spontaneous. And so remember, spontaneous reactions give off free energy, so they release free energy. So I'm going to skip ahead to slide 16 because I forgot to rearrange the slides, because after we talk about this slide, then we get into something else, then we kind of get back into the same thing we were talking about on slide 12. So that's why I'm going to skip ahead to slide 16, because here this is talking about that size and direction of the enthalpy, and so this is heat being released. So remember, this is heat released or heat absorbed. That should be a D. So that's what we're talking about when we're talking about enthalpy. So, how much heat is released or absorbed and how much disorder the system has will determine if the reaction is spontaneous, okay? And so that's why I'm going to skip all of these, because these diagrams kind of show you exactly what the slide is talking about. So I forgot to change the order, so it's my bad. But so this slide is kind of showing you pictures of heat being released, which is delta H is negative, okay? So this means delta H is negative if heat is being released, and entropy is increasing because remember, spontaneous reactions like entropy increasing. And so, with delta H being negative and entropy increasing, that makes the reaction very spontaneous. So, the arrow goes all the way out here. When entropy is increased, which is still what we want, but heat is absorbed, so this is a positive delta H, which is not what we want. We don't want to gain the energy. Remember, spontaneous reactions release energy. So that's unfavorable. So the reaction will still be as spontaneous, but like not as much. So do you kind of see what it means by it means size and direction? So, whether we're gaining or releasing heat is affecting it, and, how much, and then the change in entropy and how much. So that's, the size of the arrows in this slide. That's what that's showing you. And so here, remember, we have delta H is negative if heat's being released. And remember, that is favorable, but the entropy decreasing is not favorable. So in this top one, we have two favorable variables, and so we will get a very spontaneous reaction. Here we have one favorable and one unfavorable, so we'll still get a spontaneous reaction. And then here we have one favorable again and one unfavorable again, but they're just switched. But it's still spontaneous because of how much these arrows are going over. So if we either have two unfavorable things occur, or the favorable factor is not enough to overcome the unfavorable factor, then we will have a non-spontaneous reaction. And that's what slide 17 is going to show us. And just remember that the slide numbers are down here. So whenever I refer to a slide, it says it at the bottom. So for non-spontaneous reactions, remember heat being absorbed. So this is, delta H is positive. Because remember, this is enthalpy. So he's being absorbed, and that's unfavorable, and then entropy increasing is favorable, but the amount of heat that we're absorbing kind of overshadows the amount of entropy increase, so we're still going to have a non-spontaneous reaction. And if we go down, it's kind of, the variables are swapped, so now we have heat release, which is favorable, so now we have a delta H that's negative. But entropy is decreasing, which is unfavorable. And we had such a decrease in entropy here that the change in enthalpy, even though it was in the right direction, wasn't enough to make the reaction spontaneous. So do you see how like the strength of the arrow and the direction of the arrow really matters? Maybe if we released more energy in this reaction, then we would have gotten to a spontaneous, but that arrow would have had to go all the way this way. And so in this example, it just wasn't enough. And then for a very unspontaneous reaction, we have two unfavorable instances occurring. So we have heat being absorbed, which again is delta H is plus. And then we have entropy decreasing, which is unfavorable as well for a spontaneous reaction. And so both arrows are going in the opposite direction. So the reaction is going to be non-spontaneous. So now I'm going to go back to this just to kind of mention that this also reiterates what I just talked about, and this slide as well. So if you go through the slide, it'll tell you if you have a spontaneous or non-spontaneous reaction based on certain, increases or decreases in enthalpy and entropy. So these are both, so I'm just going to go through this super quick. So this would be both are favorable. So remember from this that delta H being negative, which is exothermic, is favorable. So H is negative. I'm just going to go through and label all my delta H's. Okay, and so we know this is favorable. We know an increase in entropy is also favorable. And so if we have two favorable things, that will result in a spontaneous reaction. Now, what happens if we have a non-favorable? I don't even think non-favorable is a word. Unfavorable. Whatever. And then increase is favorable. So here we have one favorable and one non-favorable thing. And so remember, just like in these, the favorable has to overcome the unfavorable. And so in the non-spontaneous, that didn't happen, but here that did happen because, for example, the entropy increase here overshadowed the heat absorbed here. And so, the favorable overcame the unfavorable. So that's basically what this is saying. So it says only if unfavorable enthalpy change is offset by favorable enthalpy change. And so same thing, but we're switching their variables. So in this case, this is favorable. And this is non. And so again, if the amount of decrease in enthalpy kind of overshadows the decrease in entropy, then we'll have a spontaneous reaction. So again, only if unfavorable entropy change is offset by favorable, just like those graphs that we just looked at. And then here we have two non-favorable things. So obviously if we have two non-favorable things, we're not going to have a spontaneous reaction. So this graph and those that diagram that I just talked about kind of say the same thing as this. So now we're going to talk about this thing called Gibbs free energy. And so Gibbs free energy relates to the energy that's released from a spontaneous reaction. And we're going to kind of ask ourselves, is this Gibbs free energy positive or negative in a spontaneous process? Think about that we're releasing energy in a spontaneous process. So just like if we're losing heat in a reaction and our delta H is going to be negative, if we're losing energy from a spontaneous reaction, the delta G is going to be negative. So this is our new variable. It's for, so Gibbs free energy is called delta G. And so delta G is negative. So the answer to this question is delta G is negative in a spontaneous reaction. Because remember, in spontaneous reactions, we're releasing energy. And if energy is being released, the variable is probably going to be negative because it's going away. And so Gibbs free energy is just the maximum amount of energy that could be coupled to another process to do useful work. So I already kind of touched on this way back here. Maybe I didn't. No, I know I did. I just don't remember where. Oh, here. So remember when I talked about on this slide that if you have a spontaneous reaction that releases energy, a lot of times you can couple that energy. So couple that reaction. So that means put it with another reaction that needs energy. So the spontaneous reaction will release the energy that the non-spontaneous reaction needs to continue. And so that's what Gibbs free energy is. So basically Gibbs free energy is the energy available from a spontaneous reaction that is released from a spontaneous reaction that is released and can be used in a non-spontaneous reaction to do useful work. So that's what Gibbs free energy is. It's just the maximum amount of energy that can be relayed to a different process, aka a non-spontaneous reaction that's not going to happen by itself, to do useful work and to make that reaction kind of happen. And so remember, I just kind of said that in a spontaneous reaction, delta G is going to be negative because spontaneous reactions lose energy. They release energy. So that's why delta G is going to be negative. And so this is a equation that relates Gibbs free energy, the enthalpy, temperature, and entropy. Okay, we're not going to do any examples with this, but later on when we will, this is free energy, this is our enthalpy, this is our entropy, and then this is temperature. And that's how all those are related. So delta G is equal to the amount of enthalpy minus temperature times the amount of disorder. And so I already kind of talked about these. And so now we can get onto the section quiz. And I'll kind of talk you through some of these. Some of them are harder to explain why they're wrong, but. So the first question is saying, free energy from a reaction is the amount of energy that is it absorbed by an entropy decrease, equal to the enthalpy change, wasted as heat, available to do work. So, we didn't say anything about enthalpy change being equal to any energy, so we know that this probably isn't true. We know that free energy is not absorbed by an entropy decrease. We had never said that. Free energy is just what's released from a spontaneous reaction. It's not always heat. So it's not always heat. But we do know it can do work. And so we kind of talked about that just recently when we talked about Gibbs free energy. So let's see. Yep. So free energy is just the amount of energy that is available to do work. Free energy is always available from reactions that are, so we didn't talk about endothermic reactions that much today. We didn't talk about equilibrium. So we're between non-spontaneous and spontaneous. This is kind of just about going back into your notes and looking. But we know that free energy is always released from spontaneous reactions. Non-spontaneous reactions usually require energy, like photosynthesis. Choose the correct words for the spaces. So spontaneous reactions produce blank and substantial amounts of blank at equilibrium. So we're talking about if we're releasing or not releasing energy, and if we're favoring products or reactants. So from the first couple slides, we know that spontaneous reactions do produce free energy. So we know that these are not correct. And we know that spontaneous reactions favor products, okay? So it's not going to be this. So we know that it should be A, so this should say spontaneous reactions produce free energy and substantial amounts of products at equilibrium. Yay! Which of the following involves a decrease in entropy? So remember, entropy is delta S, not enthalpy. So a decrease in entropy is getting more orderly, okay? Is something burning, is that more orderly? No, I don't think so. When dry ice subliming, so subliming is when you go from ice directly into a gas. You don't even touch the liquid phase. So if you're going from a solid to a gas, that's an increase in entropy because remember, solids have less entropy than gas. So we're getting from less disorder to more disorder. So we are increasing entropy. So we know that's not correct. And then water evaporating. So we're going from a liquid to a gas. And again, when we're going from a liquid to a gas, we know that liquid has less energy and less entropy than a gas does. So if we're going from liquid, which has less, to gas, which is more, we're increasing our entropy. So we're increasing the disorder. So we know that's not correct. So we're left with liquid freezing. And let's think about if this makes sense. So we have a liquid, which the particles in a liquid are moving pretty freely, not as freely as like a gas is. Like a gas is like this, but liquid is moving kind of freely. But then we're freezing, we're getting less energy, and we're forming a solid, which has very little energy. So that is an increase in that is a decrease in disorder, and that is a decrease in entropy. So that should be the correct answer. Yay. A reaction is spontaneous if, so these are all those conditions, okay? We have to remember what's favorable and what's not. So I'm going to go ahead and write in all my delta H positive and delta H negatives. We know that delta H positive is not favorable. Delta H negative, favorable. And then likewise, oops. No. Okay, well, I'll talk you through it anyways. Delta S increase is favorable, and delta S decrease is not. So I already said that delta, and these are just kind of rules you have to remember. I will say your test will probably, well, it will be open note, your test will be, so, as long as you have these notes somewhere, you should be okay on this kind of question. But so enthalpy decreasing, we know is not spontaneous. Enthalpy increasing is entropy increasing. Oh my God, I'm sorry. I'm reading this as delta, these are delta S's, but these are delta H's. So enthalpy decreasing, enthalpy increasing, decreasing, increasing. Entropy, this is S, so this is S that's favorable. This is delta S. This is... Okay, so this bottom one are two unfavorable, so we know this is not going to happen. This is one favorable, one non-favorable, so this might happen, but like probably not. Same thing with this is one favorable and one non-favorable, so it might not happen, but we know for sure that two favorable things happening is gonna make it spontaneous, and that's why that's the correct answer. Last question, choose the correct words for these spaces. Gibbs free energy change is the blank. Amount of energy that can be used blank, another process to do useful work. So if we look at these answers, we didn't talk about anything about duplicating. So I'm automatically going to eliminate duplicating because I never said duplicating. I did say coupling though, so this could be a possibility. So Gibbs free energy changes the spontaneous amount of energy. Energy isn't spontaneous, reactions are, so that's not right. And so we have to go to this one by default. So, but we know this is true. Gibbs free energy is the max amount. We go back here. We know that Gibbs free energy is the max amount of energy that can be coupled to another process to do useful work. And that is correct. So that is the end of today's note video. This is the last part of 18. So after today, you can expect to do some more work in your chapter 18 packets for practice. And then after we're done with the chapter 18 practice, I'll make a review video for chapter 17 and 18. And then we'll have a test, an open note test on it, probably next week at some time, probably late next week. So kind of expect that. And I hope everything I talked about made sense in this video. If it didn't, let me know and we will clarify it together.